So, in this module let us understand the asymptotic stability theorem. To solve this nonlinear stochastic difference equation, we need something called the asymptotic stability theorem. So, you did the normalization and this worked well in practice and things are stable, bounded, but how do we analyze the stability? If it is a linear system, then the stability analysis is no problem, right. We take the ordinary differential equation or difference equation that is governing it, and then you can it is a linear differential equation. So, it is no problem, because you can compute the eigenvalues, and if it is bound is less than 1, you say it is stable, right. There is no problem there, but we have a nonlinear differential equation and that complicates the matter. So, let us delve into the details of asymptotic stability theorem. We have certain conditions, we will state the conditions and we will see how those conditions apply to Oyas rule. Okay. Now, consider the general stochastic approximation algorithm, which is given by this update rule. Wn plus 1 is Wn plus eta that can depend on n times some function h that depends on the weight at time n and the input at time n, right. N equals 0, 1 so on are discrete time steps that you want to proceed till there is convergence in the algorithm. Eta is a sequence of positive scalars. In this case they are learning weights. So, it is a sequence of positive scalars. H is a deterministic function with some regularity conditions. So, I will state those conditions. Now, this is a general form of a stochastic approximation algorithm, and you can see that this function h can be replaced by the update that we had above from the Oyas update. Okay. The following conditions must be satisfied for the asymptotic stability theorem. The first condition is the sequence eta n must be a decreasing sequence of positive real numbers, and limit n going to infinity eta of n is 0, and if you take powers of eta as a function of n and sum this series, that should be finite, right. It should be less than infinity. Here one can imagine what the power p stands for. I mean, physically it basically controls the convergence rate of the algorithm, right. That is important. Now, the sequence of parameter vectors W is bounded with probability 1, because we are normalizing this at every time step 1. So, it is bounded, and with probability 1 it is bounded. The update function h, which is a function of the weight and the input, is continuously differentiable with respect to w and x, and the derivatives are bounded in time. So, this is an important regularity condition that we want to bring in. The fourth condition is the limit of h of w, which is given by h bar of w, which is limit as n goes to infinity, expectation of this function h, which is a function of w and x, exists for all weight vectors w, and the expectation is carried over the PDF of the random vector x, right, because in neural networks we are given these data vectors x, right, and when we have to take any statistics, it is over the statistics of the input data, right, and that is what this means. there is a locally asymptotically stable, in the Lyapunov sense, the solution to the ordinary differential equation which is governed by equation A. The derivative of W of t is in the limit h bar of W of t, right. And it says that there is a locally asymptotically stable, and I have not talked about Lyapunov exponents and in general the conditions for Lyapunov stability, and I will get to that little later, but take it for granted that there is a locally asymptotically stable solution to this ordinary equation. If this is condition phi, if this is satisfied, then it is one of the conditions for the asymptotic stability theorem. Okay. Let Q be the solution to this equation A with the basin of attraction B of Q. So, let me tell you a little bit about what this basin of attraction is. Now, if you think about a nonlinear dynamical system, it has several attractors or even repellers, right. So, you can imagine a river with many whirlpools, right. As you are going closer to the whirlpool, you are drawn to that particular point, right. Imagine you have 3-4 whirlpools in the river, right. Depending upon where your conditions are as you are traversing through the river or as you are going through the river, you may land up through the you may land up into a region where you are caught into a whirlpool, and this region around the whirlpool is called the basin of attraction, and the whirlpool itself is an attractor. Okay. So, this can be visualized in this diagram I have here. Now, I have these points that I mark them as blue dots, they are like my attractors, and there is a trajectory around these attractors, and this region around the attractors is distinct, and this is called the basin of attraction. Okay. Now, the parameter vector W of n enters a compact subset given by script A of the basin of attraction infinitely often with probability 1. That means, I may go with several random realizations, and if I am through this trajectory, I land with probability 1 to the attractor when I am shifting around the basin of attraction. Okay. So, this is an important result. This is not the case when you think about linear dynamical systems, right. You just look at eigen values and look at the cases when it is less than 1, greater than 1, and greater than 1 it is unbounded, less than 1 is stable, equal to 1 is oscillatory, and if it is negative eigenvalue, again you can have oscillations and bounded oscillations or unbounded oscillations, things like this. So, the analysis is pretty straightforward in the case of linear dynamical systems, not so the case when we deal with nonlinear dynamical systems. Okay. So, this diagram will help you visualize the concept. The asymptotic stability theorem states that the limit of this vector W n as n goes to infinity is q1, which is this vector q1, and this happens infinitely often with probability 1. That means, as n goes to infinity, my weight vector converges to some vector q1, and that happens infinitely often with probability 1, but it does not tell me how many iterations I need to get to this convergence. I mean, as n goes to infinity is asymptotics, right. So, it gets to q1, but is there some finite number of iterations, say capital N, that I would need such that I can guarantee this. So, this does not say that. Now, with this we are ready to embark into the stability analysis of the maximum eigenfilter, right. We had 3 parts. So, first we formulated a nonlinear stochastic difference equation based upon a normalization that was applied to the Hebbian update. Then we studied the conditions for the asymptotic stability theorem, right. What happens to the limit of this weight vector asymptotically, and given our update equation, that is from Oya's rule, we want to analyze the stability analysis with respect to this rule, considering the conditions of this asymptotic stability theorem. Okay, let us see how we can do this. To satisfy condition 1 of the stability theorem, we can choose weights eta of n, which is something like 1 upon n, right. We choose this update like this. Let this governing function h of w and x be written in this form: x n times y n. Y n is a scalar, x is a vector, vector x times y at time step n minus y square of n times this vector w of n. Now, I plug in y of n realized as an inner product between x and w. So, I get x of n times x transpose n w of n, this is my first term, and the second term, which is y square n times w n, can be written in this form. So, you must recall again that y square n is decomposed as y n times y n. One term y n is written as w transpose x, the other term y n is written as x transpose w, right. There is sort of a symmetry here. Let me call this equation B. Now, this equation satisfies the condition number 3 of the stability theorem, where it is whereby it is continuously differentiable. So, if I look at the quantities w and x and I take the derivatives, they are bounded and it is continuously differentiable, right, for as a function of w and x. Now, I take the expectation of this with respect to the PDF of x. At the very beginning I mentioned to you that the input is a stationary process. That means the PDF of the data vector x at time step n does not change with time, or the statistics do not change with time. Okay, this is very important. So, let me see how I can simplify this. My h bar is limit as n goes to infinity expectation of this messy looking equation x of n, x transpose of n, w n times w transpose n, x n, x n transposed w n and w n, right. I can put this bar down indicating it is a vector, but at this stage you should be in a position to compile if I am missing any bars underneath the variable x or w. Now, expectation is over the PDF of x. but it is not over W. So, I can pull that out. So, I have W of infinity, I pull this out, and then I have expectation over x n x transposed n, and that gives me the correlation matrix R, right. And the other term again boils down, second term again is W transpose infinity times the correlation matrix R times W infinity times W infinity, right. So, I just bring the expectation over the x's and that populates into the correlation matrix R, and the weight is evaluated at time step infinity, right. And this is very, and I could do this because my input is stationary. Otherwise, I would have a correlation matrix that depends on the time step n, and I will have complications there, right, because I have to look at locally what is happening at time step n. Okay. Now, let us go further. dWt by dt is h bar of Wt, and how did I get this, right? Because I was talking about difference equations and weights that were updated at discrete time steps. Now, the differential operator d by dt is a linear differential operator, assuming a sampling interval. My d by dt of W of t is proportional to the difference vector W of n, right. The difference vector W of n is Wn minus Wn minus 1, and this difference operation in discrete time is linked to the continuous case d by dt, the derivative, assuming the sampling interval, right. So, that is a small detail, but an important detail. So, assuming a certain sampling interval delta t, I can say that d by dt W of t is proportional to delta W of n. So, therefore, I can go from a difference equation to a differential equation, which is easier for me to analyze. So, I take d by dt of W of t is h bar of W of t. I did mention that I would like to go from difference equation to a differential equation in this case, particularly because it is a nonlinear differential equation, and it is slightly easier to tackle nonlinear differential equations than the other way around. Okay. Now, I have this is equal to R times W of t minus this quantity W transpose of t times correlation matrix R times W of t times W of t, right. Now, let me expand W of t in terms of a complete set of orthonormal eigenvectors of the correlation matrix. That is, I am doing an eigen decomposition in some sense, and I want to expand it in terms of the eigenfunctions. Okay. Now, W of t can be written as summation k equals 1 to m theta k of t times q k, where theta k is basically the time varying projection of W on q k. So, this is an eigen expansion. Q k's are my eigen vectors, and I need to have coefficients or scalars before these eigen vectors, and these scalars can be realized as a projection of W of t on q k, right, and let that be theta k of t, which is basically a time varying function. Now, I have this eigen value equation, that is, I decompose this correlation matrix using eigen values and eigen vectors. They are linked via this eigen value equation, which is R times q k, vector q k equals lambda k times vector q k, This vector qk is the eigenvector and lambda k is the eigenvalue, right, and you can realize lambda k by in this form, which is qk transposed the correlation matrix R times qk. Okay, this is straightforward. Now what we have is, going back to our problem, we are interested in d by dt of w of t, which is equal to h bar of w of t. That is the equation that we are concerned. But since we expanded w in terms of the eigenbasis, that is using those eigenvectors qk and coefficients that are functions of the time variable t, so we can simplify things a little bit. So the left hand side of this equation, dw of t by dt, is basically summation k equals 1 to m d by dt of theta k of t times this vector qk. Now I have to expand my h bar of w, and it requires two terms. If you recall, this h bar of w has two terms, r of w of t and then the second term, which is w of t transpose times r times w of t times w of t. So I have to consider all these terms. So let us do some simplifications. Let us consider w bar transposed times r times w bar. I mean, w is a vector here, so I will ignore the bar when I speak out, and when I mean w bar, I mean it's a weight vector w. So what I do is I plug in the expansion for w here. This is the eigen expansion, that is using the eigenbasis I expand, is what I have here. So in one case I have a summation L equals 1 to m, in the other case I have a summation k equals 1 to m in terms of the eigenvectors, and I have these functions theta L and theta k. Now I can do a little bit of algebraic simplification here. So I have a double summation, summa L equals 1 to m, summa k equals 1 to m. I group these two functions of time theta L and theta k together, and I have ql transposed data vector r times qk. But observe this simplification here. R times qk is basically lambda k times qk because of my eigenvalue equation. Now I pull this scalar lambda k outside, I land up with ql transpose times qk. But these eigenvectors are orthonormal, and I can write ql transpose qk as delta lk. That means it is equal to 1 when L equals to k, and their inner product, that is inner product of ql with qk, is basically 0 when L is not equal to k, right. This can help me simplify further. So this double summation is sort of got rid of with a single summation, because it just has to be evaluated at L equals k, because otherwise this ql transpose qk vanishes out for L not equal to k. So I have simplified this to summation L equals 1 to m lambda L theta L square of t. So let me call this as equation 3. Now using this equation, and my expansion for W of t in terms of the eigen basis, I can compactly simplify this in this manner, right, which you see in the terms in the above the red flower basis here. Okay. Now what we have done, plugging all these things together, h bar of W of t can be simplified as summation k equals 1 to m lambda k times theta k times q k, which is this vector, minus this summation that has minus 2 terms, and each of them is a summation, one going from L equals 1 to m, the other from k equals 1 to m. This is what I have, right. This is corresponding, again if you want to recall, this corresponds to my W of t, this corresponds to my W transposed t r times W of t. Okay. Now if I write this carefully, the left hand side is what I wanted, which is d of W of t with respect to dt, that is the left hand side, and what I have on the right hand side is basically h bar of W of t. I call this equation 4 with this simplification. Now q k's from k equals 1 to m, they are orthonormal vectors. And since they are orthonormal, by the basic property in linear algebra, they are linearly independent. So if you look at this equation 4, this is nothing but a linear combination of linearly independent vectors, right. These qk's are eigenvectors that are orthonormal. This implies they are linearly independent, and equation 4 is a linear combination of linearly independent vectors whose coefficients are governed by a differential equation. Now if I just transpose the whatever I have on the right hand side of equation 4 into the left hand side, so I get summation k equals 1 to n, summation from k equals summation of k equals 1 to m of this quantity of these vectors qk scaled by some coefficients is basically equal to a null vector. Now because of this linear independence, all these scalars that are before this vector qk, they have to be individually equal to 0, right, and therefore I land up with this equation that I can write it in this form, which is d by dt of theta k of t is lambda k theta k t minus theta k of t times summation L equals 1 to m lambda L theta L square t. So I can just equate the terms or the coefficients sticking before qk the way it is, but this detail, though it seems to be straightforward, is stemming from this fact that they are orthonormal, qk's are orthonormal vectors, which implies it is linearly independent, and then therefore you can realize this because of the linear independence. You can say that the coefficients in a rearranged form have to be 0, and that boils down to this differential equation, right, which is non-linear, sort of very straightforward here. So this works for k equals 1, 2, so on till m, and we call theta k as the principal modes of this nonlinear dynamical system. So now our goal would be to solve for these principal modes, for which we break this problem into two cases. The first case is when 1 is less than k less than or equal to m, and the other case is when k equal to 1, right. So, let us discuss the case where 1 is less than k less than or equal to m. For this treatment, I define alpha k of t as theta k of t upon theta 1 of t, right, and this holds for 1 less than or equal to k less than or equal to m. This is my general definition, but the case I am considering is for 1 less than k less than or equal to m, right, for all k not equal to 1. And theta 1 of t is not equal to 0 with probability 1, and the weight at time step 0 is randomly chosen according to some distribution. They are small random values. Now, our governing equation is d alpha k of t. So, what I do is alpha k is theta k upon theta 1. Now, I do a d alpha k of t upon dt. So, I take the derivative of alpha k. So, it is straightforward from my chain rule. It is I treat 1 upon theta outside, it is derivative of theta k minus I take theta k and then I apply the derivative on theta 1, which is going to be 1 minus 1 upon theta 1 square of t times d theta 1 of t upon dt, right. So, this looks sort of messy the way I have written it down, but let us simplify. So, we have two terms here. This is term 1 and this is term 2, right. I simplify term 1. So, what I do is 1 upon theta 1 of t, I pull it outside. Now, d theta k of t upon dt, I expand it out. I have done this derivative earlier. So, therefore, it is basically lambda k times theta k of t minus theta k of t times summation L equals 1 to m lambda L times theta L square of t, right. I have gotten this from my governing differential equation there. Now, for the second term, I pull theta k of t upon theta 1 square of t outside and just focus on this term here, which is d theta 1 of t upon dt. So, all I have to do is replace k equals 1 in the equation 5a that I have written above. So, I just plug that in for k equal to 1 straightforwardly and I land up with equation 5b. Okay, is nothing but k equals 1 I have lambda 1, k equals 1 I have theta 1 and I just take this forward, and the last summation L equals 1 to m remains as is. Now, let us see how this can be simplified. So, basically I sum the terms in equations 5a and 5b. So, if you see on one side I have minus theta k of t upon theta 1 that is appearing before this summation in 5a, and in 5b appearing before the summation is plus theta k upon theta 1, right, if I do the simplification. So, basically the summation cancels out and all we land up is in a simplified form, which is theta k upon theta 1 times lambda k minus lambda 1. So, d alpha k of t upon dt is basically alpha k of t times lambda k minus lambda 1. So, what is the interpretation here? I mean, besides all this algebraic jugglery, right? Why did I happen to do this? Now, recall that these theta i's are functions of time that are sticking before this eigen expansion, eigenvectors in the eigen expansion, and we want to sort of evaluate the relative um, strengths of these functions of theta evaluated with respect to the first component. That means I take this function theta as a function of t for the first eigen component, which is q1, right, and I want to scale that relative to any other k which is not equal to 1. That is sort of what the idea is, and would it head to 0 or is it non-zero? This is what I want to infer from this study, right, and that is the reason why I am doing all this. Now theta k upon theta 1 is alpha k, and I can write this is lambda k minus lambda 1. So since lambda 1 is my maximum value, that is this is the maximum eigenvalue, and lambda 1 is greater than lambda 2 is greater than lambda 3, so on, I would like to write it in the form of minus of lambda 1 minus lambda k. So lambda 1 minus lambda k is basically a positive quantity, and I have this alpha k that I have it as is. So my governing difference equation is d alpha k upon dt is minus of lambda 1 minus lambda k times alpha k of t. Now assuming my eigenvalues of the correlation matrix are distinct and I have lambda 1 lambda 2 in the descending order, the term lambda 1 minus lambda k is proportional to 1 over the time constant, which is positive, because lambda 1 minus lambda k is positive and this is a time constant which is proportional. This quantity lambda 1 minus lambda k is proportional to 1 upon the time constant. So you have an equation of the form d alpha upon dt is minus a times alpha, right, this is how it is. So d alpha k by dt is I just write d alpha by dt. Let me put the k there to avoid the ambiguity where k is not equal to 1, and a is this positive quantity which is given by lambda 1 minus lambda k, right. Let us just focus on this box that I have here on the right hand side. Now this is a simple linear differential equation whose solution alpha k is e power minus a times t subject to some initial condition, right, u of t. Now as time goes to 0, so let me put this time variable as well here. So as t goes to infinity, alpha k of t dives to 0, right, this is obvious. So therefore for all principal modes from 1 to k where k not equal to 1, this function dives to 0. That means I do not have any other mode except possibly the mode k equal to 1 that I need to investigate. Okay. We will stop here and we will continue with the other case when k equal to 1, and that is more tricky because we require Lyapunov analysis towards that, and we will study that in the next lecture.